Okay, so we've been talking chapter 13 gases last time we got into. We hit a number of gas laws, right? And we talked about three very common units of gases, which is an atmosphere, which is 1 atm, 760 torr, and 760 millimeters of mercury. As we talked about last time, there are other pressure units, but I would say these are the common sort of three pressure units that we come across a lot. And obviously, that 760 number is the number to convert between torr, or millimeters of mercury, and an atmosphere. Remember also a torr and a millimeter of mercury are essentially the same thing. It's a one-to-one sort of conversion between them. We talked about some different gas laws. We talked about Boyle, which was P1 V1 equals P2 V2. We talked about Charles' law, which is V1 T1 equals V2 T2. We also saw Guy-Lussac's law, which is similar, P1 T1 equals P2 T2. As we also talked about, really pretty much if it is a gas law, no matter what gas law it is, always pretty much temperature's got to be in Kelvin, regardless of sort of what they give you and what they ask for you in terms of units. We also saw our friend Avogadro, I think, and Avogadro there, V1 N1 equals V2 N2. Here, N is the moles of gases. Putting all those guys together gave us the ideal gas law, which is PV equals nRT. The ideal gas law there is the most restrictive in terms of units. So always when you're using the ideal gas law, it does need to be in atmospheres, the pressure. The volume has to be in liters. Moles should be in moles, and temperature needs to be in Kelvin. And really, for that reason, is the gas constant, which is R, is 0.08206 liters times atmosphere, Kelvin times mole. So these are the units associated with the gas constant, and that's frankly why everybody else in the equation needs to be in those units so everything cancels out correctly. As we also talked about, R is just a number that is usually, I would say, pretty much most of the time not given to you anywhere in the problem, not mentioned anywhere in a gas problem. It's just assumed that you kind of know that you have that value available to you. So as we talked about last time, again, if you feel like you're missing some other number, it may be R, and like I said, not usually mentioned at all in questions. We also talked about STP, which is standard pressure and temperature. And remember that when you are given STP, the temperature value is 273.15 Kelvin, and the pressure is 1 atmosphere. So they are actually giving you those values that you could use. And if you needed to use them in the ideal gas law, that's obviously what you would put into the ideal gas law for pressure and temperature. We did see an important relationship as well, which is when you're at STP, you can use this conversion of 1 mole of any gas will equal 22.414 liters. So that is a conversion factor that can be used only again at STP conditions. And what it oftentimes will allow you to do is, bless you, not have to perhaps use the ideal gas law. So you can kind of use it in place of the ideal gas law in certain situations. And those certain situations has to be STP conditions. So if it is not STP conditions, you should definitely never use that conversion. You should use the ideal gas law. In fact, you could always use the ideal gas law pretty much in any situation. It is kind of like a universal sort of gas law. So you use it at STP conditions, non-STP conditions, whatever conditions it may be, you could go into the ideal gas law. So as I think we might also talked about last time, if you just want to forget about that conversion, you really don't need it because you could just go into the ideal gas law with 273.15 as your temperature and your pressure being 1 atmosphere. We finished up, I think, talking about an important gas law, which is the combined gas law. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. And we talked about that this gas law here, and really kind of like this version of this gas law, which is P1 V1 over N1 T1 equals P2 V2 over N2 T2. It's a really good one to invest your time in, sort of remembering, because frankly, you could get pretty much all these gas laws up here from it. All you have to do again is basically cross out whatever is not given to you, not mentioned, or it's held constant in a problem. So once again, if you had no mention of moles or temperature, all you would do again is just cross out the bottom part there. And now you have Boyle's law, which is, what you would probably use in that particular problem. Again, if you had this, and no mention of pressure or moles, you could just, again, cross it out on both sides. And now you would have Charles' law, which again, which would be probably what you would need to use. So remembering maybe this version of the combined gas law. And as I mentioned earlier last time as well, this guy and pretty much your ideal gas law will pretty much give you any gas law that you would probably need to use, or you could get to it really easily by doing so. Any questions on that there? Okay, so I don't think we did the example with that, so let's try the example here. Consider a sample of oxygen gas at 27 degrees Celsius. We have a volume of 9.55 and a pressure of 297. We change the pressure to 8.25 and we heat it to 125. What will be the new volume of the gas? Take a few moments there and see what you come up with here. Okay, so let's take a look at it. So as we talked about last time, a lot of times with gas problems, it's a really good idea just to pull out the information and label it. So we obviously have a temperature at 27 degrees Celsius. We have a volume that's 9.55 liters, and we have a pressure that is 2.97 atmospheres. We got another pressure here of 8.25 atmospheres. We have a temperature there of 125, and we are looking for a volume. So again, just by labeling everything, it should really point you in the direction of the combined gas law, as obviously we have two pressures, volumes, and temperatures. Once again, it really doesn't matter which ones you call ones and twos, but we'll call the first set here ones, if I know how to do one there, and these guys twos. In terms of units of our pressure, they're both in atmospheres, which is good. Again, they got to be the same. Our temperature, like normal here, we do need to convert, so we'll add 273.15, and that's going to get us a 398.15. And we'll also do that over here for our first temperature, and we'll go that way there. Give us 300.15. So now that we have it all sort of everybody in the right units, we can take our P1 V1 T1 is equal to P2 V2 T2. In this particular case, we're looking to solve for our V2. Remember, quick way to rearrange, it's just opposite locations. So he's going to go up and he's going to go down there. And that will get you everybody in the right spot. That'll get you P1 V1 T2 divided by T1 P2 equals V2. We're basically multiplying and dividing in that case, multiplying the T2 and dividing the P1 there, or P2 to the other side. Putting our numbers in the right spot here. We got our P1 there, which is 2.97. We have our V1, which is 9.55 liters. And again, T2 goes up on top here, 398.15. All divided by our T1 on the bottom, which is not that, 300.15. And our P2, which is 8.25. In terms of units here, atmospheres on top and bottom cancel, Kelvin on top and bottom cancel. Leaves us just liters left over, which is good since we're looking for a volume in this case. 2.97 times 9.55 times 398.15 divided by 300.15 and 8.25 there. Going to get us a 4.56 liters as our volume. Any question on that one there? I would say probably again, in a lot of cases, this one gives people a really difficult time sometimes, just in terms of rearranging thing and making sure, everybody gets to the right spot. It's a very common mistake. People reverse numbers and stuff like that. So as I might have mentioned last time, if rearranging the equations is problematic for you, take some time to figure out how to, again, properly rearrange it. And then the easiest way is just opposite. So always when you move across the equal sign, it goes to the opposite location. And whatever you're solving for always needs to be up on top by itself. Yeah, so that's the important thing. Everybody's got to be up on top by itself. Any questions on that there? Yeah. So we're going to then talk about stoichiometry that involves gases. And the good news about stoichiometry that involves gases is, frankly, it's the same 4 steps or that we've been talking about when we talk about stoichiometry problems. The only additional sort of step that you do a lot of times is somewhere along the way, you're going to insert probably the ideal gas law or gas law in there, but most of the time it's going to be the ideal gas law. So we still want to make sure, again, we have a balanced equation. We still want to really convert to moles. We still want to think about whether or not we are dealing with a limiting reagent problem like we've talked about previously. Then we want to go our mole to mole relationship from the equation. And then we want to take our moles to some other unit. So I will say pretty much where this will maybe vary from a normal stoichiometry problem is because we're dealing with gases, we will probably be using the ideal gas law. And there's really kind of 2 spots where you would use the ideal gas law. Probably the most common spot or popular spot would be at the end, because a lot of times, like the experiment we did last week and the experiment you'll do this week, you're oftentimes interested in how much volume of gas you collected. So a lot of times at the end here, we'll use the ideal gas law and actually solve for volume, which would be nRT divided by P. I would say the other place where commonly as well that you could use the ideal gas law is actually over here. And again, you would be using it to solve for moles in this case, which would be PV over RT. So that's another place where you would use it instead of grams to moles or something like that, using the molar mass. You would actually use the gas experiment there to actually do that. For example, you could have done that in the last experiment that you did in the experiment. You could use all your experimental values, your pressure, your temperature, and your volume, and solve for the moles, and then did a mole to 22.414 liters to get it in STP, or moved it over and did it with the combined gas law as well. So there's a couple of different ways you could sometimes use these sort of situations, but I'd say probably most commonly at the end, and occasionally as well at the beginning, and sometimes at both times you may use it beginning and end. Any questions on that there? So let's take a look at one together here and just kind of go through the steps and see what's going on. So here we want to know what volume hydrogen gas do we need to react with 5.65 grams of phosphorus. So really, if we think about hydrogen gas, which is obviously our gas here, so we should think about gas laws. We want to know what volume of it. We do have a temperature that's 27 degrees Celsius. We have a pressure that is 1.25 atmospheres. And, we could think about stoichiometry here. PV equals nRT. A lot of times is the gas law that you're going to use. So if we think about it, we got pressure, we got temperature. We're looking for a volume. Remember that we always have R, even though it may not be mentioned anywhere in the problem. So you always have that value given to you. So we can see that in terms of the hydrogen gas here, in order to get to the volume, we are missing the moles of the hydrogen gas. And that's essentially where the stoichiometry part comes into play. So we can think about, like, we kind of already use these guys. So really the only other piece of information that we have in this problem is the grams of phosphorus we're starting with. So we're really just going to do a basic stoichiometry problem here to figure out how many moles of hydrogen using stoichiometry, so that we can then use the ideal gas law at the end of it. So to do that there, we would need perhaps phosphorus here, 3097 on the periodic table. So here again, we're just going to follow our steps. This is a balanced equation, which is good. We're going to take what they gave us and convert to moles. So we're going to take our P4 and get the molar mass, which would be 4 times 3097. And that's going to get us there. 4 times 3097. 123.9. So just like a normal stoichiometry problem here, we'll start with our 5.65 grams of P4. We'll use the molar mass from the periodic table, 123.9 grams per mole of P4. Grams will cancel. Going to get us our moles here of P4, which looks like 0.0456. Oh, there. Moles of P4 in this case. All right, so now that we have P4, remember though that we do need to get to hydrogen, which is the gas here, and that's really where the stoichiometry part of the calculation can come to. So we're going to look at the relationship between those two guys so that we could go from our P4 to our hydrogen. And from the equation, we see that we have 1 mole P4 gives us 6 moles of hydrogen. So that is what we're going to use to do the conversion here. We'll take our number, 0.0456 moles of P4, using the mole-to-mole relationship. 1 mole P4 gives us 6 moles of hydrogen. And that means times 6 here, 0.2736. So this stoichiometry part up until this point allowed us to get to our missing piece of information that we needed for our ideal gas law. So now that we have that, we're ready to go in the ideal gas law, except we do have to check some units now that we have the moles of our hydrogen. In terms of units, everybody's good except for kind of like our temperature there. So again, a 27 plus a 273.15. Gonna get us there. 300.15. In this case here, we're going to solve for volume, which is nRT divided by P. Putting in our number 0.2736 moles, our R value. And our temperature, all divided by our pressure in this case of 1.25 atmospheres. Atmospheres will cancel, Kelvin will cancel, moles will cancel. Once again, we're left with liters, which is good since that is what we're looking for, a volume. So we'll take our moles, we'll times it by 0.08206, times it by 300.15, and divided by 1.25. Looks like a 5.39 liters here of hydrogen in this case. Any questions on those steps? So once again, hopefully you can see it's pretty identical to a normal stoichiometry problem. Obviously as well, this was not a limiting reagent problem because we did not have enough information to get to moles of each of those things, and we weren't looking for anything on the product side. So it's just really just a basic stoichiometry problem where essentially at the end there, instead of using the molar mass, we went into the ideal gas law. Any questions on that? Like normal, you could, again, just kind of go from one step to the next without getting an answer in between if you wanted to, obviously, as well. All right, so I tried one. Why don't you try one here and see what you come up with? That's what we just did. All right, let's do this one, which is essentially the experiment you did last week. You took some magnesium, low hydrochloric acid. Bubbles hopefully happened, yeah. Calculate the volume of hydrogen gas produced at STP if you started with 5 grams of magnesium and use excess amount of HCl, magnesium 2431. All right, stick a few moments there, see what you come up with here. Definitely got an equation. We do have STP, so a reminder that that is actually 2 values. So our temperature here would be 273.15 Kelvin. Our pressure would be 1 atmosphere. So we could think about hydrogen gas here, which is what we're interested in, and probably our P equals nRT. We are looking for the volume here. And once again, we do have R always, so 0.08206 liters, atmosphere, Kelvin, and mole. So once again here, we do have temperature, R, pressure. We're looking for volume. Just like in the previous problem there, we are missing really the moles here of hydrogen in order to use our ideal gas law. So that's where, again, the stoichiometry part's going to come into play. They were also nice enough to tell us that this is the excess reagent, right? So we don't have to worry about any type of limiting reagent type situation happening here. That means the magnesium is our limiting. This is going to be our balanced equation. We will then convert into moles. So we'll take our 5 grams of magnesium using the molar mass there from the periodic table, 2431 grams per mole of magnesium. And if you got an answer at this point here, we'll call it 0.2057. So that is the moles of magnesium, but once again, in this case, we do want to go from magnesium down over to our hydrogen, since that is the gas we're interested in here. So we will do that, and we can see it's a 1 mole magnesium, gives us 1 mole of hydrogen. So that math doesn't seem too bad here. So 0.2057 moles of magnesium. Doing our stoichiometry here, 1 mole magnesium, 1 mole of hydrogen. Moles cancel, gives us 0.2057 moles of hydrogen. That again is essentially the last piece of information that we need to use the ideal gas law here. We're ready to actually solve for our volume. And again, here we could go into our ideal gas law. Volume would be nRT divided by P. Putting in our moles, 0.2057, our gas constant, and our temperature, all divided by our pressure, which in this case is a 1. Atmospheres again will cancel, Kelvin will cancel, moles will cancel, leaves us liters. And in this case, it looks like here we're going to get 4.61 liters of hydrogen. This would be your theoretical yield in this case, much like calculation you could have done on the experiment last time. And that's how much you produced in this case. Any questions on those steps there? Now, in addition to using the ideal gas law, we could, if we wanted to, also solve this another way, and that is because we were at STP. So this would be a situation where you could properly use that relationship of 1 mole of any gas is 22.414 liters at STP. That means you could have just picked up right there without using the ideal gas law and just use that as a conversion factor. Moles will cancel, and you'll get there as well. So you could have done it either way. As you can see here, a good reminder that you could always use the ideal gas law, so you don't have to worry about that conversion. But if you remembered it, you could use it without using the ideal gas law. They both should give you the same here. Any questions on that there? Question on stoichiometry involving gases. Pretty much the same steps. Throw yourself in there an ideal gas law or something like that somewhere along the way. We also talked about stoichiometry when we were talking about Avogadro's law as well. So remember that if you do have a sort of pressure and temperature that are constant, which is essentially what Avogadro's law is all about there, which is V1N1 equals V2N2. Remember that you could take an equation, as we saw there, And if it is at constant pressure and temperature and you're just interested in a volume and you're given a volume of a gas, like say the volume of C was 3 liters, and you want to know how much A you started with, how much liters of A. In this case, because it's at constant pressure and temperature, we actually can skip all kinds of gas laws. We can skip really mole to mole relationships, and we can do, as we saw earlier, I think in this chapter, a volume to volume relationship between these two. So, for example, here we could say 1 liter of A gives us 4 liters of C, and we could use that again, just like a mole to mole relationship, and we could just do the calculation like 3 liters of C. 4 liters of C and 1 liter of A. The liters of C will cancel. And in this case here, we would have started with 0.75 liters of A. So again, that's another sort of variation on stoichiometry. Again, a specific situation has to be pressure and temperature being constant. And if you're just like a volume to volume sort of relationship, you could just do it like a mole to mole relationship and bypass any type of gas law and stuff like that, and it'll come out the same. Any questions again on that? I think we saw that earlier on in this chapter. Yeah. Okay. All right, the next thing we're going to talk about then is the idea of Dalton's law, partial pressures. And it sounds really difficult, but it's not too difficult here. But the idea of partial pressures is when you have a mixture of gases, which is very common that they do kind of come in mixtures of different gases together in the same container, we could apply sort of partial pressures. And the very sort of simple idea of this is if you had a container and inside that container is only gas molecule A, and obviously, as gas molecule A is flying around, the total pressure, like your barometer reading, would be equal to really only the pressure as a result of gas molecule A as it's flying around. Now, if you had a container where you had gas molecule A, gas molecule B, and gas molecule C basically flying around in there, when we look at the total pressure of this sort of mixture of gases, it's really a result of the pressure of gas A plus the pressure of gas B plus the pressure of gas C. And these are what are referred to as being partial pressures. And they're partial pressures because when you add them all together, they give you the overall pressure of that mixture of gases. So what is a way that we could calculate really the partial pressure of a gas in a mixture? Pretty straightforward. Most of the time, it is our friend the ideal gas law is what we're going to use. And we would solve for pressure, say of gas A. We would do the same calculation with the pressure for gas B, and so forth, gas C, or however many we have. Now, one of the nice things about this idea is because all those gas molecules are in the same container, they pretty much will all have the same volume. And because that container is sitting in the same room on the same shelf, they will all have the same temperature as well, which means when you're doing the pressure calculation for each of these gases, really the only thing that's going to probably vary between the gases is the moles of each of those gases that are present. The temperature will be the same for everybody in that mixture. The volume will be the same for everybody in that mixture as well. And when you do this calculation individually for each gas, that is basically going to give you the partial pressure of each of those gases. Now, the reason we could really do this is one of the reasons that makes something an ideal gas is the idea that even though it may be in a container with other gas molecules, there's pretty much no interaction between gas molecules. So even though there may be all 3 of these gases, A, B, and C, flying around in that container, because we're in an ideal situation, we could treat each gas as almost being in there by themselves. So all the other gases will have no effect on the other ones that are flying around in an ideal situation. And that's why, again, we could kind of do these calculations individually for each of them. And the only thing that will basically affect the overall pressure is just adding them all together at the end. So that is probably the most common way that you can calculate the partial pressure of a gas is, again, just simply doing an ideal gas law calculation for each gas individually. And to get the total pressure, just simply adding them all together. As you can see here, that's what we just talked about there. Now, what's up there? We'll talk about it, I guess. Probably we won't run across it too much in this class, but as you continue on in your chemistry career here, there may be some situations where maybe you're not given enough information, for example, to calculate the pressure of a gas in this situation, because they maybe don't give you the temperature or they don't give you maybe the volume or things like that. So there is another way that if you know at least one piece of information, either you know the total pressure of all the gases in that mixture, or you know one individual partial pressure, and you're able to get to the moles of all the gases, you could use this equation here to calculate partial pressures. And this is what is referred to as the mole fraction. And a mole fraction is really like a percentage without times it by 100. We take the moles of what you're interested in, and we divide it by the total moles of the gases that are in that mixture. We just don't times it by 100. So you can use this formula down here. This is the partial pressure of a gas. This is the mole fraction for that gas. And this is the total pressure of that mixture. So for example, let's just say that we had a total pressure of, we'll do 1.5 atmospheres. And we had 2 moles of A and 3 moles of B in a mixture of gases together. So if we want to know, say, the partial pressure of A, we could use this because, frankly, we don't have temperatures given to us. We don't have volumes, so we can't use the ideal gas law. So if we wanted the mole fraction of A, that would be the moles of A in this case divided by the total moles, which is 2 plus 3, which would basically give us 2 divided by 5 in this case. And if we do that, 2 divided by 5, going to give us 0.4. And that is the mole fraction basically of A. It's basically 40% A flying around in that container basically, and 60% of the other guy basically flying around. So the mole fraction would be that. So the partial pressure of A in this case would equal our mole fraction times the total pressure. And here, if we take 150.1.5 times 0.4, will tell us that basically the pressure here of A is 0.6 atmospheres. So this is a way that you could actually calculate the partial pressures, as long as you could get to the moles and also the total pressures. By the way, the pressure of B in this case, in my made-up example, would then be the total pressure minus the pressure of A, which means 1.5 minus 0.6 atmospheres, going to give us 0.9 atmospheres in this case. And that's the way you could find the pressure of your other gas. Or you could also do the mole fraction of your other gas, which in this case would be 3 divided by 5. And in this case, 3 divided by 5, 0.6. And we'll take our pressure there, 0.6 times 1.5, and that should give us 0.9 atmospheres. So this is a nice little sort of formula that occasionally, you're maybe not given enough information to go into the ideal gas law. And as long as you got the moles of each of those guys, and again, just one piece of information about pressure, either total or a partial pressure, you could really find the partial pressures of everybody else. Any questions on that? I will say you probably won't see too much of that in our class, but in your next class, you definitely will. For us, probably using the ideal gas law is going to be the way you're going to calculate partial pressures. Any questions on that there? All right, I think we'll lay it up there for today.